Hello students. In this video we are going to see how to find the magnetic field inside a solenoid using Ampere's circuital law. In the last lecture we had seen how to find the magnetic field due to a current carrying conductor using the Ampere's circuital law. In this case we are studying about a solenoid. So this is a typical solenoid that you would have seen earlier. What is a solenoid? Solenoid is nothing but a conducting wire which is wound in form of coils. Okay, so this is a closely wound long helical conducting wire. We can pass current through this coil. Like in this case, the current is flowing in this direction. So the current is flowing through the coil, through all the turns the current is flowing, because of which this solenoid will start acting as a bar magnet with the north pole of the magnet on this side and south pole over here. Now we are going to find the magnetic field in the between or in the center of this solenoid or inside this solenoid by using Ampere's circuital law. Now in this diagram what is shown is a solenoid which is a real solenoid. It is not an ideal solenoid. What is a real solenoid? In which this is the length of the solenoid and this is the radius of the solenoid. So length is not very large compared to the radius. This is a normal solenoid which we use in normal applications. For our derivation, we are going to consider an ideal solenoid. What is an ideal solenoid? In ideal solenoid, the turns of the solenoid are closely spaced. They are very close to each other. The length of the solenoid is much greater than the radius of the turns. So, in an ideal solenoid, these turns are not so far apart. They are very close to each other, and the length of the solenoid is very much greater than the radius of the solenoid. And another important thing of this ideal solenoid is that the magnetic field inside the solenoid is constant or is uniform, and the magnetic field outside this solenoid is negligible. We assume that the magnetic field outside the solenoid is negligible, that is, it is so small that it can be ignored. We can assume it to be zero. So we are going to say that the magnetic field inside this solenoid is uniform, but outside this solenoid the magnetic field is zero. Now let's see how we can apply Ampere's circuital law to find the magnetic field inside this solenoid. Now I have drawn a cross section over here. Okay, let me just explain in this case itself. So we have current flowing through this solenoid from this direction. The current is flowing like this. So if I consider this point over here, how is the current flowing? The current is flowing inside, right? So I can show it by a cross. Then the current will come through the coil and it will come out from this particular point. So that I can show by a dot. Is it not? The current is coming out. When the current is going in, we can show it by a cross, and when it is coming out, we can show it by a dot. So throughout this solenoid, the current will go in through this top part and it will be coming out in the outward direction in the lower part. So I can draw a cross section of this solenoid in this way. Okay, in this particular solenoid, the current is coming out from here, from this particular loops, from the top part of the loop, and it is going in through this lower part. It is going in through this lower part. Okay, so I have shown the magnetic field lines inside the magnetic field is uniform. That is, the magnetic field lines will be evenly spaced. We have evenly spaced lines to show a uniform magnetic field. And outside, the magnetic field is nearly zero because we are considering an ideal solenoid. Now, again, I have simplified it further. So I have just drawn the dots and the crosses. Okay, I have not shown the field lines, magnetic field lines. I have just shown the dots and the crosses. Now we have to find the magnetic field because of this solenoid at the center or somewhere inside the solenoid. So suppose I want to find the magnetic field at this particular point P. Okay, I want to find the magnetic field at this particular point. So what do? I'm going to consider a loop, an Amperian loop, according to my convenience. Now, a circular loop is of no use to me right now. So I have considered a rectangular loop or a square loop, whatever, such that one part of the loop is inside and other part of the loop is outside. I have just seen that, or I have assumed a loop such that it is enclosing the current flowing through this solenoid. So I have just taken the loop to enclose certain turns of this wire, of this solenoid. Okay, so now let's see. Suppose small n is the number of turns per unit length. Per unit length of the solenoid, the number of turns is small n. Small I is the current flowing through the coil. Now we have assumed an Amperian loop which is in the form of a rectangle or a square. You can just say anything. Now what is the first step? How do we apply this Amperian law? We are going to find the closed integral or the line integral of b bar dot dl. Now this b bar dot dl, this is not a continuous loop, is it not? This loop I can divide into 4 parts. What are those 4 parts? First part is this AB, then the part BC over here, then CD, and again this AD, So I can divide this into 4 parts. So I'm going to take the integral b bar dot dl over this 4 regions. That is, integrate from A to B, b bar dot dl, plus integral from B to C, b bar dot dl, then C to D, and similarly D to A. Okay, that is how I have taken the integrals. Now just see, I will just consider the loop from A to B, that is this part. We are considering this part. Okay, now in this case, what is the direction of B? The direction of B, see, throughout this inside the part of solenoid, the direction of B is constant. So the direction of B I can show like this. B is directed in this way. DL, what is the direction of DL? DL is also directed in this, is it not? So what will I get? Integration of A to B, B dot dl, theta is 0, so cos theta is going to be 1. So I am going to get this as B integral dl, okay, because integration of b bar dot dl bar is b dl cos theta, and cos theta is 1 since theta is 0, right? So I get b integral A to B dl. Now see the next part, that is from B to C. From B to C, if you consider, that is this region, if you consider this part, What is now the direction of B? The direction of B is this. B is in this direction, and dl is in this direction. This is the direction of dl. So theta is equal to 90 degrees. So B bar dot dl bar, that is B dl cos theta, is going to be B dl cos 90, and cos 90 is 0. So this term is going to be 0. It is going to be 0 because B bar and dl bar are perpendicular to each other. That is, angle between them is 90 degree. And if angle is 90 degree, cos 90 is 0. So it is, the dot product is going to be 0. Similarly, for this part, from D to A, it is going to be the same thing because B is acting in this direction. DL is acting now in the downward direction. DL is acting downward because we are traversing the loop in anti-clockwise direction. So DL is downward. Anyways, the angle between them is 90. So integration from D to A, that is this term is also going to be 0. Now what about this CD, the loop CD? This loop from C to D, or this part of the Amperian loop from C to D, is there any magnetic field over here? No. The DL I can show like this. DL is like this, parallel to CD. But the magnetic field outside the solenoid is 0. We are considering the case of an ideal solenoid, and so outside the solenoid magnetic field is 0. If magnetic field is 0, this entire term is going to be 0. Right? So we have only one term which is contributing, that is B, integral A to B dl. Now what is this integration of dl? Integration of dl is going to be integration of this part. Integration of this part from A to B. So suppose this length is L. I am considering the length L. So integration dl will be capital L. So I will get the answer for integral B bar dot dl bar is equal to B into L, that is BL. Okay. Now what are we supposed to do? We are going to equate this to mu naught I, because that is what is our Ampere's law, that integration of B bar dot dl bar is equal to mu naught I. So I get BL is equal to mu naught I. Now what is this I, this capital I? This capital I is the current that is enclosed by this loop. Current which is enclosed by this loop. I have to find out that current now. I don't know what is that current, is it not? We know that the current flowing through each coil or each turn is small I, because that is the current flowing through the coil. So if I have n number of turns per unit length, and L, capital L is the length of this coil, that is AB, then number of loops or number of this turns of this coil enclosed is how much? It is going to be N into capital L. This is the number of turns in the Amperian loop, And if I is the current through each loop, I can say that the total current flowing inside the Amperian loop is number of loops into the current through each loop. So I'll get it as NLI. So in place of this capital I substitute NLI. So what is the equation that I get? I get B L is equal to mu naught N L I, where N is the number of turns per unit length, capital L is the length of the Amperian loop, small I is the current flowing through the coil. So by solving this, L on both the sides is going to get cancelled, and what do we get? We will get the magnetic field inside the solenoid is equal to mu naught Ni. What is so special? What do you note over here? That it is not dependent on the distance from the edge. Okay, there is no distance related over here. The magnetic field inside a solenoid is depending only on the number of turns and the current flowing through the solenoid or current flowing through the coils. So what does that mean? Again, it proves that throughout the solenoid, the magnetic field value is same. Whether you are taking the magnetic field closer to this or at the center or at the edge over here, everywhere magnetic field is having the same value. Implies magnetic field is uniform inside a solenoid. Okay, so this formula is for ideal solenoid, is it not? We have derived it for ideal solenoid because we have considered the magnetic field outside the solenoid to be 0. But we can apply this formula for real solenoid also, provided we are using it at the center. At the center means over here. If we are using it at the center of the solenoid, means at this particular place, if you are finding the magnetic field, yes, we can use this formula. But at the edges, you cannot use it. Okay? And we can find the value of D, or we can convert this solenoid into a magnet of the magnetic field, giving a magnetic field that we require, having a value B, by choosing the number of turns and current flowing. So this is the equation for magnetic field inside a ideal solenoid using the Ampere's law. So see, it just involves 3 steps. You just have to consider the Amperian loop and find out the integration of that dl and equate it to mu naught I. That's it, and you get the equation, right? So this is for solenoid. Now let's see for a toroid. What is a toroid? Toroid is something very similar to this solenoid. Only thing is, in solenoid these coils are kept straight. In toroid, again we curve or we make them into a circle. Okay, so this is the diagram shown. See how is the current flowing. The current is entering from here, going inside over here, coming out from here, again going inside, coming out, going inside. So if I have to show the direction of the current, how am I going to show it? See, it's going inside over here, so I'll put a cross, coming out, so dot, going inside cross, coming out dot. So I can just put all crosses over here because it is same. The current is coming out, going in from here and coming out from the top part. Okay, so I can show it this way. Now let's find the magnetic field inside this toroid by using the Amperian loop, right? So now again, suppose capital N is the number of turns of the toroid. Capital R is the radius of the Amperian loop. Suppose this dotted line, blue dotted line, is the Amperian loop that we have considered. I have taken capital R as the radius of the Amperian loop. And small I is the current flowing through this coil. This small I is the current flowing through this coil. Now, we have chosen an Amperian loop which is in between. So see this. I have shown this toroid over here. Those cross marks are here. because the current is going in from here and coming out from these points. Okay, we have chosen an Amperian loop somewhere in between like this. Okay, so now for toroid though, it is very simple. What we have to do, we have to find first integral b bar dot dl. So find integral b bar dot dl, that is equal to integration b dl cos theta. What is the direction of b? Again, the direction of b is like this. This is the direction of b. Okay, because it is nothing but acting like a solenoid. So similar to solenoid, we will get the direction of b. dl is a small length, so it is also acting in the same direction. So I will get theta is equal to 0. So cos theta is equal to 1. So this becomes integral b dl. So b comes out because b is constant everywhere. This Amperian loop is a circle, right? So this b comes out and integral dl. So integration of this dl is what? It is 2 pi r, because see, it is a circle with radius r, capital R. So I get integration b bar dot dl bar is b 2 pi r. Now equate it to mu naught I. That is our Ampere's circuital law, is it not? So b bar dot dl bar is equal to mu naught I. What is this b bar dl bar? It is b into 2 pi r, capital R. That is equal to mu naught. What is I? Capital I is the current which is enclosed by this Amperian loop. What is the current enclosed by this Amperian loop? That is this current over here. Is it not? And what is that current? If small I is current flowing through each loop and n is the number of turns. So this loop is enclosing all the turns now. Now I need not see the number of loops per unit length, because this Amperian loop is enclosing all the turns of the coil. Is it not? It is enclosing all the turns. So I can just write capital I, that is the current enclosed by this Amperian loop, is equal to number of turns into the current through each turn. So I get it as Ni. I can replace this I by Ni. Okay. So I get the equation for B as this 2 pi r goes here in the denominator, and I get it as mu naught Ni upon 2 pi r. Now see, this magnetic field is depending on r. It is inversely proportional. So as r is changing, as the distance from the center, this r is changing, the magnetic field is also going to change. More the r, lesser is going to be B, right? It is inversely proportional. So we see that the magnetic field is depending on r, right? So in this way, we have used the Ampere's circuital law and found out the magnetic field due to a toroid. Thank you.